The projectile motion simulation. Projectile motion describes the motion of an object that is launched in the air and moves under the influence of gravity as the force that's acting upon it. The simulation ignores resistance. The simulation also involves Newton's second law, as it pertains to projectile motion. Newton's second law states that the motion of an object depends on the forces acting upon it, which is where the force equals mass times acceleration equation comes from. In projectile motion, gravity produces a constant downward acceleration. Gravity only acts vertically, so the motion of the object can be separated into horizontal and vertical components. The projectile motion simulation demonstrates how objects move through the air when they are launched at an angle. Projectile motion is an important concept because it plays a role explaining the motions of an object such as cannonballs, rockets, basketball shots, and cornhole. The simulation will show how one can change different variables and observe how they affect the path of the projectile. First, we're going to look at angles. So what I'm going to do now is change the angle to 20 degrees. In the simulation, I launched the projectile at different angles, 20 degrees, 45 degrees, and 70 degrees, while maintaining a constant velocity. And the trajectory of the cannonball changed each time. So we're going to do 20 degrees. Wow. At 20 degrees, the motion was primarily horizontal and the height was very, very low. Now, we're going to do 40 degrees. Wow. At 45 degrees, the projectile was horizontal and vertical. And it was also balanced. So the horizontal and vertical components were balanced. And at this angle, the projectile had the longest range. And now we're going to do 70 degrees. Wow. At 70 degrees, there was very high vertical motion and a shorter horizontal difference. And to explain this, when the projectile is launched, the initial velocity splits into horizontal and vertical components. A larger vertical component corresponds to a greater height, and the object is in the air for a longer duration of time. When you increase the vertical component, it decreases the horizontal component. At 45 degrees, the components are balanced in a way that maximizes the horizontal range. So now we're going to change the velocity. So we're going to start with the velocity where it is, and then go. Wow. Now we're going to go at a higher velocity. Okay, so changing the initial velocity, what that does is when launch velocity is increased, the projectile travels farther. It reaches greater heights and stays in the air for a longer amount of time. This is because velocity affects motion because it determines the projectile's initial kinetic energy, and a higher velocity means greater kinetic energy and a greater horizontal and vertical velocity component. Velocity remains constant during flight. Increasing initial velocity increases the range of the projectile. The time the projectile remains in the air is also affected by the vertical component of velocity. If the projectile moves upward at a very fast pace, as it did when the initial speed was 23 meters per second, it will take gravity a longer time to slow it down. And we can see that again if we increase the velocity one more time. So by increasing the velocity, it takes gravity a longer time to pull it down. Now we're going to talk about gravity's effect on trajectory. As I was doing the simulation, I observed regardless of the launch of the angle or velocity, projectile always curves downward, creating a very parabolic-like picture. The curvature occurs mostly because of gravity. Gravity constantly accelerates the object downward. The gravitational force is what we call weight. During flight, the horizontal velocity remains constant, but the vertical velocity changes over time, which is what we saw here. When the trajectory is at its highest point, the vertical velocity becomes zero, and gravity accelerates the projectile downwards, which is how the projectile lands on the ground. Basically, one direction has a constant velocity and the other has a constant acceleration, allowing for the projectile to follow a parabolic path, which is what you see in the simulation.
I will now explain drag using the simulation. When we are working with items traveling through our atmosphere, we must take into account the opposition force of drag, or air resistance. The drag equation tells us that drag is equal to the drag coefficient times 1/2 the air density times the velocity squared times the cross-sectional area of which the drag coefficient is based. You can see here on the NASA website. In this case, our item is a cannonball. And we can see here that the drag coefficient of spheres, where did it go? Right here. See here that the drag coefficient of spheres is 0.47. We can make a prediction based off of the drag equation. Seeing that we multiply by the cross-sectional area of the object, our drag coefficient will be greater when the object is bigger. So if we launch two items of the same weight but varying sizes, the bigger object should travel less far due to the greater drag forces opposing its movement more strongly. Let's start with a 5 kilogram cannonball with a diameter of 0.5 meters. Wow. Okay, now let's only change the diameter to be 1 meter across. Wow. Our hypothesis was correct. The larger cannonball didn't travel as far due to air resistance/drag. Air resistance obviously has to do with air, but why does it happen in the first place? Air resistance creates a drag force because while an object is moving through our atmosphere, it collides with the gas molecules in its path. This is why objects with a larger surface area experience greater drag. They run into more air particles because they take up more space. Also, while the force of weight always points in the same direction, the direction of the drag force is always changing because it is always opposite of the direction in which the object is moving. You may have heard that the air is thinner at the top of Mount Everest or another tall place. This is because there are less air molecules at higher altitudes. Fun fact, this is why Canelo Alvarez and other athletes train in the mountains like Lake Tahoe. Less air molecules equals less oxygen molecules. Training in a lower oxygen environment makes your cardiovascular system work harder. So Canelo has better endurance when he goes to fight at a lower altitude with more oxygen in the air. Anyways, less air molecules means that drag forces are lower because items traveling through the atmosphere don't collide with as many molecules. We can test this within our simulation. As you can see here, there is an altitude bar so that we can change the altitude. We will launch a cannonball at an altitude of 0 meters. Yup. Now we will launch it at an altitude of 2,000 meters, similar to that of Lake Tahoe. And according to what I just told you, the cannonball should travel further this time. Oops, not 5,000. I said 2,000. Yay! Physics wins. We were right. Goodbye.
Yay!